looks like when I started the recording. If you catch me on a day where I forget to start this, let me know, because I'm going to try to remember to do this for all of our classes. And what I'm going to talk about here today is not necessarily anything you really even need to take notes on. So you can if you want to, but basically what I'm going to do is we're going to talk about some prior knowledge things that you learned about in geometry or algebra 3-4, and about how those are going to relate to this course, trigonometry. So anything that we talk about here is in specific relation to trigonometry. I would plan on having to reteach. Okay? And this is just kind of like blanket prior knowledge review. Yes? Certainly. Okay with that? So nobody, don't worry about too much notes. You can if you want to, like you're encouraged, that's fine, no big deal. I don't think you need to, but that's kind of what we're going to do right now. Okay with that? So the title for this course is Trigonometry. The root word for this is, what does it look like if you're trying to break this word down to understand what it meant? There's like two parts to this word, right? What would the two parts be? Anybody? Just shout these out, man. This goes a lot better if you're willing to give it a shot. I know it's the end of the first day and you're like kind of fried. Trig. And the second half would be ometry. Okay. If we think about the first half, what do you think trig is referencing? Triangles, I heard somebody whisper. Shout them out loud if you know it. Take credit for when you have good ideas. That's right. And ometry at the end, referencing like study of. Yeah, exactly. So what we're really talking about here are triangles. So that's how I want to preface our thought back to our prior geometry knowledge. So if I think back to geometry and I'm thinking about triangles, what are some of the facts or theorems or formulas or definitions or vocabulary from our geometry class that's relevant to talking about triangles? Yes, Lucas. Okay. We have three sides. Okay. That's good. What else do we got? Ben. Okay, so let's call this maybe SOHCAHTOA. Most of us, I hope, are familiar with this acronym. What is this acronym really telling us? It's telling us that sine, that's the S, is opposite over hypotenuse, that's the OH. Cosine, that's the C, is adjacent over hypotenuse, that's the AH. And tangent, that's the T, is opposite over adjacent, that's the OA. Most of us, I hope, have seen SOHCAHTOA before, right? Most of us would have thought about this, hopefully, in your top 5 big triangle ideas from your geometry class, and I know that was a long time ago. So when we say opposite, hypotenuse, adjacent, what are those in reference to? What do we mean by opposite, hypotenuse, and adjacent? Trevor?
Well, you find the hypotenuse and the other one adjacent from it, whatever side is it. So you find the longest side, which is the hypotenuse, whatever side is adjacent.
The longest side of what object? Okay, what kind of triangle?
Right triangle.
Okay. So these opposite, hypotenuse, and adjacent are all sides of a right triangle. So if this is my angle X here, and I call these sides A, B, and C, or I'm sorry, those vertices A, B, and C, what side is my opposite?
So one, not the bottom one, the one to the left.
So using two letters,
AC.
AC. And which side is the adjacent? CB. And which side is the hypotenuse? AB. So when we've defined sine, cosine, and tangent in geometry class, this was always in reference to a right triangle. Hi. Thank you. Jackson. Is everybody okay with that idea? This is one of the first things that we're going to deal with when we get into trigonometry, is we need to broaden that definition of where here we're restricted to working with angles inside of a right triangle. We would like to be able to use sine, cosine, and tangent for more than just a right triangle situation. That's one of the first things that we're going to need to deal with when we start in on trigonometry, is extending that definition so we can deal with not just a right triangle situation, but really any angle. In this situation where we're stuck inside of a right triangle, that value that we can have for x is bounded. There's a limit to how big or small that value for x can be. What is that limit right now? So this value of x is an angle measure inside of a right triangle, right? What does this value of x have to be between? The low end should be easy. 0. Thank you. And the high end is 90. Very good. Why can't it be bigger than 90? Ben? Great. So that was a theorem from geometry. We called that the triangle Sum Theorem. I wouldn't have expected anybody to call that by name, but knowing the interior angles of a triangle, add to 180 degrees would be an expectation that we kind of remember. Hopefully, now that we say it, you're like, oh yeah, I remember that being true. If you didn't remember it right away, that's okay. So the way we've defined sine, cosine, and tangent, we can only use it for values of x between 0 and 90 degrees. What we're going to do in this course is we're going to broaden that definition for sine, cosine, and tangent, removing this right triangle requirement so that we can really pick any value of x that we'd like. So negative infinity to positive infinity is where we'd really like to be at. So it's going to require a little bit redefining of what we're doing here. But that's one of the first things we'll look at. Okay? So another question here. We said that sine is opposite over hypotenuse, right? Why did we choose to define sine as opposite over hypotenuse? Why not hypotenuse over opposite? Is there any good reason why we might not want to have defined it as hypotenuse over opposite? I'll give you a little hint. Think about the relationship between the length of the opposite side and the hypotenuse side. Is there any general thing you can say about their lengths when compared to one another? Ben?
Well, it wouldn't come out right if you had a hypotenuse over opposite.
What can we say about the relationship between the hypotenuse and the opposite? Just about their lengths. Allison. Yes. So the hypotenuse has to be always at least as big as the opposite side. There could be a situation in a non-right triangle where they're the same length, but the hypotenuse can never be shorter than the opposite, right? So if I have a number in the numerator of my fraction that's always bigger than the denominator, what could happen there? What can we say about that fraction? What will its value always be greater than? While that, what you've said is true, it will be greater than 0. There's another number it will also be greater than. What? 1. Right? If the hypotenuse is always bigger, or at least as big as the opposite, you're always going to have something like 4 over 3, or 5 over 2, or you'll always have something bigger than 1, right? In the case of opposite over hypotenuse, we have a limit of how big it can be. How big is, if we had opposite over hypotenuse, what is the upper bound on that got to be? Ben? It's the same answer. 1, right? So if opposite over hypotenuse is always going to be 1 or smaller, hypotenuse over opposite will always be 1 or bigger. What's the problem of getting 1 or bigger? Infinity, right? Infinity is involved in 1 or bigger. 1 or smaller, because we're talking about side lengths, you're bounded between 0 and 1, so your ratio can't get out of control large there, which I think is probably the motivation for selecting sine and cosine as opposite over hypotenuse and adjacent over hypotenuse respectively. But that's not really a fantastic reason once we've removed the right triangle as the basis of our definition, which we will do later. And it turns out we will go ahead and define 3 more trig functions, one of them being hypotenuse over opposite, hypotenuse over adjacent, and then adjacent over opposite. We'll call those the reciprocal trig functions because they are the reciprocals of these fundamental trig functions. We'll talk about that, though, in detail later. But there's not really, with a new definition, allowing any values of x, there's not really a great reason why we select just these ones, other than like some convenient calculation things, like your values for sine and cosine are bounded nicely, rather than being unbounded, where we can go to infinity. Okay, let's think. There's another important triangle fact, maybe triangle theorem that I'm sure that every single person in this class knows and has used many times. Allison? Pythagorean theorem. Very good. And the Pythagorean theorem says a squared plus b squared equals c squared. But what are a, b, and c? They're the side lengths of what kind of triangle? Right triangle. And which sides can A, B, and C just be any side for that triangle? Is there anything special that goes on there? C has to be the hypotenuse. The other sides, A and B, you could label either leg as A or B. That part doesn't really matter. Everybody okay with that idea? The key here, though, is the Pythagorean theorem only works on right triangles. Would it be nice to have a version of this that works for any triangle? Yeah, that would be nice, right? In fact, if you think hard, we already saw briefly, if you took geometry at Notre Dame Prep, that other version of the Pythagorean theorem where you can use in a non-right triangle. Does anybody happen to recall that formula? So we talked about the law of sines. The law of cosines is the different version of the Pythagorean theorem, but we also have the law of sines, both of which we use in non-right triangles. If we use them in a right triangle, the law of cosines just turns into the Pythagorean theorem, and the law of sines just kind of doesn't make much sense. But, yeah, so there's that. And again, depending on where you did your geometry and how good your memory is, maybe you remember these names. I'm sure you probably don't remember the formulas, which is fine. I would not expect that. We will re-derive these formulas from scratch, assuming nobody has seen them before. But you may recognize the name. Once I started the law of, a couple of people kind of seemed like they had familiar with the name at least. But you probably spent 1 or 2 days in your geometry class 2 years ago talking about it. So if you don't really remember, you're entitled to not remember that. That was a long time ago and not much time spent there. Probably some vocab still worth talking about with respect to triangles. Does anybody remember some triangle-specific vocabulary? Yeah, and I apologize here as I'm sure I'm going to spell this wrong. Maybe is that how you spell it? I'm not positive. Nobody laugh at me later when they watch the video and they're like, that's not even close to right. I think it's kind of close. Good, so isosceles is one. What's another? What are some other triangle-specific vocab like that? One that starts with an E, yes. And then a Q, equilateral. Okay. There's right triangles. No, that's one. There's some more. Acute, I heard somebody say. I mean, that's kind of how I remembered obese is like, it's the big triangle. Obese is like obtuse, I guess. And there's one more that I can think of that I would expect to have listed here. Starts with an S, scalene. And one more that I would have been surprised to have listed, that's equiangular. Let's just kind of review what these things mean again, because although we remembered the names, maybe we didn't really remember what they mean. Isosceles means?
No, that means like
Two of the sides are the same. Equilateral?
all the sides.
Yep. Right? One right angle. Acute? All of the angles are less than 90 degrees. Obtuse? One angle greater than 90. That probably doesn't look that obtuse, huh? That's maybe a little better. Scalene? All three sides are different lengths. That's all that means. So like a 3, 4, 5 triangle. Equiangular? Yeah. Now, two of these are really the same. Which two are really the same? Equilateral and equiangular are really talking about the same thing. If you remember, there was a theorem from geometry that says that the angle and opposite side length in a triangle are proportional. So if all the side lengths are the same, all the angles have to be the same, and then vice versa. So that relationship holds. That's good. That's probably good for our geometry review of topics. So Algebra 3-4 topics. One of the things that we're going to be doing in this trigonometry class is extending our definition of sine, cosine, and tangent into thinking of these as functions. So let's review here quickly what the definition of a function is, and then talk about some of the attributes we have to describe functions that we spent a good amount of time in Algebra 3-4 kind of talking about these things. Does anybody remember the definition for a function? I know it's been a minute. Yeah, that's a decent shorthand. So a function is a set of ordered pairs where each x pairs with exactly one y. So when we talk about a function, oftentimes we want to have ways to describe kind of the properties of that function. And we spent a good deal of time at the beginning of Algebra 3-4 kind of talking about some of these properties. I'll start because, well, it may be a little vague what it is that I'm asking for, but domain and range is an example of a property of functions that we've talked about for every type of function that we had last year, right? We were always interested in the domain and range. That'll still be the case when we extend these operations of sine, cosine, and tangent and turn them into full-blown functions. We'll be interested in their domains and ranges. What else? What other attributes or properties or descriptors did we have that we used to talk about functions last year? Anybody feeling brave, wants to venture a guess? Yes, Lucas. Yeah, that's a great one. So, end behaviors. So included in that, maybe I'll include horizontal asymptotes or slant asymptotes would be included inside of end behaviors. That's an excellent one. Very good. Okay, and by intersections, I'm really going to say intercepts, like x and y intercepts. But yes, that's a good one. Katie, you got something for us? Dig deep. Come on, you got something rattling around in there other than just one that begins with a D. Odd or even, yeah, that's absolutely one. Thanks, Brent. So let's just pause there for 1 second about because I do want to talk about what odd or even means, because this was something we touched on for like a day during first semester, and if you're like, what in God's name do you mean be odd or even? Unless you're talking about 2 is even and 3 is odd, I don't really know what you mean. Which is fair, because we didn't spend oodles of time on this, and it was a year ago. So we say a function is odd if f of negative x is equal to negative f of x, and we say it's even if f of negative x is equal to f of x. Basically what we're saying is if the graph of the function is symmetric about the origin, it's odd. And if the graph is symmetric about the y-axis, it's even. So we have like an algebraic definition and then like a geometric definition. Depending on the context or the information that you're given, either one of those might be the useful way of thinking about it. Discontinuity might have been the D1 you were thinking about. That is another good one. So the discontinuity involved vertical asymptotes and the removable discontinuities were both examples of discontinuity. The vertical asymptote is an infinite discontinuity is the way we describe that. As opposed to removable discontinuity, it's just like the hole in a graph, basically. So those are good ones. Yep. Trevor, you had said union at one point, which we used to help describe domains. So I'm going to kind of just include that in the domain topic. And then you had said, what did you say after that? You had another one that you were chiming in with. No? Vertical line test, which is how we determine if something is a function or not. Which, again, relevant. I'm going to include that inside of the function topic. Allison. Sure. You can have positive or negative. We say a function is positive when it's above the x-axis and negative where it's below. Along with positive or negative, it could also be 0 when it's on the x-axis. With that, we have increasing and decreasing and constant. So a function is increasing as if you have your little man and you're walking along the graph. If your little man is walking uphill, people that had me last year remember me talking about the little man walking on the graph. Yeah. So like this guy is increasing for the entire graph, because if you move from left to right, the graph is always going up, as opposed to this one where we're decreasing here and increasing here. We're also constant there at the bottom of the valley, where the graph's slope is basically 0 there. So that's what we mean by increasing, decreasing, and constant. With increasing and decreasing and constant, we often talk about maxes and mins. So the bottom of a valley is a minimum and the top of a hill is a maximum. We can talk about the global maximum, like the highest of the high points, or the global minimum, the lowest of the low points. Or you can talk about the locals, which involves any hill or valley, basically. What else here? I think we talked about concavity. So a function can be concave up or concave down. So this one would be concave up, because if I tried to fill this with water, the function would hold water. This one would be concave down, because if I tried to pour water on that, the water would run off. And you can have functions that are both have parts that are concave up and concave down. So example here, this part of our function is concave down. If I poured water on that, it would run off. And this part of our function is concave up. If I poured water there, it would kind of catch it. And this spot in the middle where it changes concavity is called the inflection point. We talked about this just ever so briefly in Algebra 3-4. This is a topic that you'd spend a fair bit of time with if you took calculus next year. And you'd learn how to do or define the intervals in which a function is concave without actually even having to look at the graph. But to do that, you need some pretty good calculus tools to be able to do that. It's not trivial, but it's also not terribly difficult to do. But beyond the scope of this class. But that's a kind of going forward. Let me think. Oh yes, there's a couple more. We talked about the inverse functions. And we'll spend a good amount of time talking about inverse functions in trigonometry also. If you remember back to geometry, if you wanted to find an angle inside of a right triangle, what did you need to use? Like sine inverse or cosine inverse or tangent inverse, right? If I wanted to solve for an angle inside of a right triangle, as opposed to solving for a side length where I could use sine, cosine, or tangent. You guys remember that? Now, we had a special property that was that we talked about alongside when we talked about inverse functions, because oftentimes we were concerned that the inverse for our function might not be a function itself. The property there that we're concerned with is whether our function was one-to-one. What this meant was that we had no repeating y-coordinates, so that each x paired with exactly one unique y. If our function is one-to-one, we know its inverse is going to be a function. If our function is not one-to-one, our inverse would not be a function. Now, the way we've described sine, cosine, and tangent in geometry and tying those to right triangles, those are functions. They're one-to-one. The inverses would be a function. We don't have a lot to worry about. in trigonometry where we extend our definition to allow us to take the sine, cosine, or tangent of any angle, these new sine, cosine, and tangent functions are no longer one-to-one. So we have to be a little bit careful when we build our inverse, because we need to do it in such a way that we're getting a function back out that we can program easily onto a calculator. So these inverse functions on our calculator have to be a little bit careful with how we're using them so that we're actually getting the answer that we are looking for. And we'll talk in great detail about that later on this semester when we talk more about once we've extended the definitions and start building out what these inverses really look like. Trying to think if there's anything else here. This is probably a good, the most of it. I'm sure there's a couple of things that I can't think of off the top of my head, but this is a great first start.